Okay, let's dive right into this explainer and uncover the absolutely jaw-dropping math that actually powers your daily commute. I mean, think about it. Every single day, millions of us hop in our cars, pull out our phones, type in a destination, and just blindly follow that blue line that pops up on our screen. We take it completely for granted, right? But the invisible system operating underneath that digital math, it's literally one of the most stunning achievements in modern computer science.
To truly appreciate what your phone is actually doing, I want you to imagine standing in New York looking all the way towards San Francisco. Now, across the North American road system alone, there are roughly 64 million intersections. If you tried to calculate the absolute shortest path by just brute forcing it, checking every single option, there are roughly 10 to the 220th power possible routes. Just to put that into perspective, if you could check a billion routes per second, testing all of them would still take over 10 to the 200 years. So yeah, it is an incomprehensibly massive problem. And this brilliantly illustrates the sheer magic of modern computing, because somehow your phone can sift through that impossible number of options and hand you the absolute perfect route in about 4 seconds. That's literally less time than it takes to buckle your seatbelt. So how on earth is it bypassing 10 to the 200 years of calculation in the blink of an eye? Well, the answer lies in a brilliant piece of logic that was actually formulated over half a century ago. To understand how we do this today, we actually have to travel back to 1956 Amsterdam. Meet Edsger Dijkstra. He was working on software for an early computer called ARMAC. Now get this. At the time, the general public considered computers to be practically useless. In fact, computing was so obscure that when Dijkstra tried to file for his marriage license, the municipal authorities flat out rejected programmer as his profession because, well, it didn't legally exist yet. He actually had to settle for putting down theoretical physicist. Because of all this, he desperately needed a highly relatable problem to prove the worth of his new computer to regular everyday people. While he was thinking about the absolute shortest way to travel from Rotterdam to Groningen on a map of the Netherlands, he realized something crucial. Simply counting intersections, like stepping from one node to the next, just wasn't enough. Not all roads are the exact same length, right? So he needed a method to calculate the actual distance, or what programmers call the cost, between points. Basically, he had to keep track of the absolute shortest distance from the starting source to any given node on the map, which would allow him to systematically build up shortest paths, step by step. So the whole crucial point here comes down to the logic of Dijkstra's algorithm itself. Imagine you start at 0, and you just assume everything else out there is infinitely far away. Then, you explore your immediate neighbors and update their distance, or their cost. Now, the real genius part is that you always move to the unexplored node with the lowest current cost next. By systematically fanning out from the lowest cost nodes to the highest, Dijkstra's algorithm fundamentally guaranteed that you would always find the absolute shortest path to your target. Why? Because by the time you actually reach your destination, you've naturally exhausted any possibility of a shorter route even existing. But here is what's absolutely wild. This foundational algorithm, the one that still powers huge parts of our digital world today, was entirely conceptualized during a coffee break with his fiancée. Seriously, he did the whole thing in 20 minutes, entirely in his head without using a single pencil or piece of paper. As he later pointed out, designing without paper almost forces you to avoid all avoidable complexities. He coded it up, it worked perfectly during the computer's public demonstration, and just like that, it quietly became one of the most elegant mathematical concepts in history. However, as incredibly elegant as Dijkstra's math is, we run into a major scaling problem today. When you scale that beautiful math up to the massive North American road system, a search takes about 7 seconds per path. Now, 7 seconds doesn't sound terrible if it's just you, but when millions of people are asking Google Maps or Apple Maps for directions at the exact same time, it creates massive server bottlenecks. To actually serve the world effectively, modern mapping algorithms need to run in under a millisecond. So to solve this speed issue, programmers started trying out other iterations. See, pure Dijkstra searches outward in a spreading circle, meaning it explores exactly the wrong direction just as equally as the right direction. To fix that, they developed the A-star algorithm. A-star uses a heuristic, basically a math penalty, for any path that moves away from the target's general direction. It essentially forces the search to head straight toward the goal. But here's the catch. While A-star is fantastic for calculating raw physical distance, like in a video game, it actually loses to a well-tuned Dijkstra when you optimize for the shortest travel time. Travel time requires evaluating speed limits and nasty square root computations, which just makes A-Star way less efficient for our modern driving apps. Okay, so what if we tackled this huge search space from a completely different angle? Think about this. What if you run the search from your starting point and your destination simultaneously? The two searches basically grow toward each other and meet in the middle. Because the area of a circle grows exponentially, two smaller spreading circles cover significantly less total area than one massive circle. This bidirectional search cuts the processing down dramatically, but it still doesn't inherently understand human logic. Like taking a fast highway instead of a winding local backroad. Back in the early 90s, GPS systems actually tried to encode that human intuition by manually tagging highways and local roads. Human surveyors would classify the roads, and the computer was told to search local roads first and then quickly jump up to the highways. But as you can probably guess, this was deeply flawed. If the designated search area for those local roads was too small, the system might force you onto a highway when a series of local roads was actually way faster. It just couldn't reliably guarantee the true shortest path every single time.
And right here is where we finally hit the ultimate modern shortcut: customizable contraction hierarchies. It's a bit of a mouthful, I know. But look at it this way. If we had a massive lookup table of every single route perfectly pre-calculated, it would take up petabytes of data and literally take decades to compute. If we use pure Dijkstra, it's just too slow. This algorithm, though, it's the perfect middle ground. It automatically preprocesses the map to rank the importance of intersections, giving us insanely fast query times without having to pre-calculate literally every single route in advance.
So you might be wondering, how does it actually rank that importance? Well, in the pre-processing phase, the system recursively looks for small clusters of intersections that essentially split the map right in half. Think of a bridge connecting two towns. Basically, everyone has to use it, so it automatically gets the highest rank. When you zoom out to a continental scale, the algorithm naturally identifies massive geographical bottlenecks, things like the handful of bridges over the Mississippi River or key passes through the Rocky Mountains. Mathematically speaking, these become the absolute most critical nodes on the network. Once it ranks all these intersections, it runs through three vital phases. First, it orders the nodes. Second, it adds what are called lower triangle shortcuts. Basically, it evaluates local roads, and if a cluster of minor roads creates a faster path between two major roads, it just draws an invisible mathematical shortcut connecting them. Finally, when you ask your phone for directions, it runs a bidirectional search that only travels upward into higher-ranked roads. By layering these calculated shortcuts right on top of the node rankings, the computer can just completely ignore millions of irrelevant residential streets while absolutely guaranteeing it hasn't missed some sneaky, faster backroad shortcut. And the payoff of this hierarchy is just absolutely staggering. Let's say you're mapping a massive road trip from San Francisco all the way to Montreal. Standard Dijkstra would have to evaluate millions of nodes. A bidirectional search definitely helps, dropping that down to a few thousand. But this elegant contraction hierarchy collapses the search space so drastically that it only needs to check 1,236 nodes. Most of the nodes it checks are really just the local streets right around your house and the ones right around your destination in Montreal. The rest of the country is just completely bypassed. Because the algorithm only has to check the most important, pre-calculated bottlenecks once it gets high enough in the road hierarchy, this entire method operates in about 200 microseconds. Let that sink in. That makes it a staggering 35,000 times faster than a well-tuned standard Dijkstra search. It's literally the perfect marriage of human geographical intuition and raw computational efficiency, and it's exactly what makes our global routing apps even possible. Yet beneath all this mind-bending modern optimization, beneath the petabytes of server processing and real-time satellite traffic data, the core engine driving your navigation remains Dijkstra's algorithm. That simple, elegant, 70-year-old math, formulated by a guy just drinking a cup of coffee in Amsterdam, still dictates the fundamental logic of how we traverse our physical world today. As Dijkstra himself famously said, simplicity is prerequisite for reliability. You see, Dijkstra believed deeply that the human programmer was entirely accountable for the elegance of their work, not the machine. He absolutely hated sloppy code and avoidable complexity. He actually once remarked that if, years in the future, an engineer was doing something quick and dirty and suddenly stopped to think, Dijkstra would not have liked this. Well, that would be enough immortality for him. His true legacy is that relentless pursuit of doing things beautifully. So, the next time your phone calculates a cross-country trip in under 4 seconds, take a brief moment to really look at that blue line. Appreciate the 70 years of brilliant human ingenuity working silently right there in your pocket. And ask yourself, how can you bring just a fraction of that thoughtfulness and mathematical elegance into whatever work you leave behind for the world?